All right. So this is our start to chapter 6, work and kinetic energy. Work and kinetic energy. First thing to might come to your mind is work is like just something that's you do, you go to work. Something takes work to do. How can you describe work? In the term we're going to use it as, it will be referred to as, let me first, what is work? It will be referred to as, just the amount of energy that's required to apply a force onto something. We've been, covering forces. First, we went from motion, things just moving, and then we went into forces. Something has to be applying a force in order for something to change its acceleration. But now we're going to sort of take another step back and say, well, something's applying a force. How much energy does that take in general? So let me give this little definition. The amount of energy required to force an object. The amount of energy required to force an object over a distance. This is kind of my version of the technical definition. Force an object over a distance. Okay. Work is it's just a value. It's an amount of energy. So when I say work, I'm just meaning energy. How much energy does it take to push this box along this ramp? Things can now, with me using the term work and defining energy, I can now sort of say like, that will take this amount of energy out of the system, or I can put energy into the system. Work is a scalar quantity. So that means it's just a value. There's no like forces are sort of directional. They're vectors. Work is just a value. Energy can either be put into a system or out of the system. So positive, negative, or zero. Let me give the, you might also hear, like if you watch other YouTube videos on work, say work is force times distance. So let me first write that one down. So work is force times distance. I'm going to say the magnitude of the distance. So this is the final distance minus initial. This is correct to the most point. What I want to emphasize is on this though, is that work is specifically force times whichever direction the distance is being moved. What do I mean? If something is being forced at an angle, I can ask, what is the work amounted to, if I'm pushing something up a ramp, the amount of work required to lift the object would just be sort of going from the bottom of the ramp to the top. So it's related to the direction it's going. So let me, in this little sidebar, I'll say in the direction of the displacement. In the, this is how we're able to say this is a scalar quantity. It's a work within sort of this limited range. We could say it's positive or negative within the terms of a problem. I'll do a little example problem in just a minute. The direction of the displacement of the displacement. Okay. Last thing, like while I'm on this equation for work, I can write out what the units are. What are the units of work? What are the units of energy? Well, energy will be, I just say like units. The units of energy are joules. So I'm going to go like straight down. I'll say work. That'll say like 1 joule. Joule, it's just a J as the unit form, is equal to 1 Newton. See, that's right underneath the force times 1 meter. So these are the units, or what a joule is made out of. Work can be done on an object or by an object. What do I mean by this? This is sort of where the scalar factor comes in. So I said it could be positive or negative or 0. The example they give in the book is a spring, stretching a spring. And I think at first I didn't like the example, but I'm sort of leaning towards it now. Let me sort of explain with a little picture. So we have a first case and a second case. So before, the spring sort of sits here. So I'll just say like before. Doesn't quite matter. I'm not going to put any values on this. And I'll say I'm going to stretch this spring. And so its natural point is this length, but I'm going to stretch it outwards like this. And it will become this second image over here, sort of stretched. And it's going to be, if you've done this before, it's kind of tense. We can say there's more energy in this system. This is like an intuitive example. There's a lot of tension, a lot of force just holding it out at this stretched point. So I'm going to say by applying a force, let's say by applying a force over a distance, work is done on the spring. Work is done on the spring. And by doing work on an object, there is positive work being added into the system. So it's just me saying I'm adding energy into the system. So say the energy of the system the energy of the system increases. Okay, so I can do work on an object. I can stretch a spring. I can lift a box, or give something a push by adding energy to the system. Whatever I'm calling the system, whatever I'm sort of zooming in on with my bubble, and I draw the force free body diagram around. Things can also be work can also be done by an object, and work done by an object is negative. We have the same exact sort of picture. But we start out with this stretched spring. I'm holding it already, and it's just a value. It's not important at the moment. I just know it's tense right now. There's a lot of energy in the system. But then I am going to sort of bring it back down, slowly decrease it until it's back at its resting state, so that it's at, this second image over here. So I'm going to say, by removing some force over a distance, by removing some force over a distance, work is done by the spring. And I can sort of finish this off in the same way by saying the energy in the system, since it's doing, since the spring is doing work, work done by the spring, the energy of this system decreases. The energy of the system decreases. So that means it's sort of giving away some of its energy. It's applying work on its surroundings, so it's getting rid of its energy. Okay, I'll do a quick example of this. We have a 3,000 kilogram truck. It's being lifted by a crane and placed onto like a cargo ship. This crane is lifting this this truck with a certain amount of upward force, and it's lifting it. It sort of lifts it up to a height of 2 meters. What we want to know is, what is the work done on the truck by the crane? Second thing is, what is the work done on the truck by gravity? And finally, what is the total work done on the truck? Let me go down here. And first off, you can always draw a free body diagram to begin with. Picture, or just go right into the free body diagram. We'll make this one just a cube. And so here's our truck, and it's being lifted upward with a force upward. And I'll just say force from the crane. Okay. There's also, in this free body diagram, there's a force downward due to gravity. So F sub G. First question, what's the work done by the crane? Work done on the truck by the crane. So start out with work by the crane is equal to the force applied from the crane over the distance that it is applied. This is specifically how high up is it raising it. So delta Y. In this case, it's simple. We got all of the values for this already. 31 kilonewtons and 2.0 meters. Turns out we get 62 kilojoules as the result. Next up was the work done on the truck by gravity. Same sort of arrangement. Work done by gravity is the force of gravity over how far the truck is displaced. Well, the force of gravity, we need to break this up a bit more. So we have mass of the truck times acceleration of gravity multiplied by displacement, which then also goes straight into 3,000 kilograms. Force of the acceleration of gravity is downward and is negative. This is where we'll input a negative sign, minus 9.8. And for reasons of sort of introducing newtons into this equation, I'll say newtons per kilogram. That's also what a G equals times its displacement. That equals minus 59 kilojoules. Okay. And finally, what is the total work done on the truck? That's where we just add up all of the work from all of the forces that are at play. So work total, that's just work of the crane in this case, plus the work from gravity. 62 kilojoules minus 59 kilojoules. We get a total work done on the truck as it's being lifted of 3 kilojoules. Okay, so we have, this way of measuring how much energy is being applied to this truck as it's being slowly lifted. We have, the work it takes just to lift it in general. That's the amount of energy the crane is giving. It's trying to lift it. The amount of energy that's gravity is trying to pull it down, and they sort of counter each other. So in general, as we raise this truck up a bit, it gains energy. We'll get more into why it's gaining energy as it sort of raises up. That'll be what's called potential energy. We'll get to that in a couple chapters from now. Actually, we're going to look at one type of energy. Let's go over kinetic energy. This will be the last page, then we'll get you guys started. So we have this sort of way to, connect energy to work. First off, we need to know what is energy. We're saying work is an amount of is energy, and it's force over some distance. So how can we define energy? We hear this all the time, and we get energy or uh, power bills. There's those two things are actually slightly different. I will get to that when I go over power later in this chapter. But what is energy? How can I just define it in this case? Let's say that energy is a way to see how much work can be done. A way to see how much work can be done by a system. So earlier in that example problem, I said a truck. So it was the exact phrasing. So it was said, what is the work done on the truck by the crane? So the crane is sort of giving some energy to the truck. We want to know what is energy. It's a way to see how much work can be done by a system. How much energy can a crane offer to other things? That's sort of relating it to that previous problem. There are many different types of energy. We'll get into several other types later on, but for right now, we're going to talk about kinetic energy. We're learning about work. It's a force that is, over some distance. A force changes an object's acceleration. So we're saying that an object will be moved some distance. So this object is going to, at some point, be in motion. How can we relate what we've learned in the second chapter, just learning about motion? How can we connect some rules of motion to energy itself? Do we always have to go step by step, velocity and then acceleration, and then we have to find a force, and then we have to then go into work just to find the energy? Can we sort of, instead of making it 4 steps, can we just take those two ends and relate them directly like that? So we don't every time have to find all of these, terms. We can start out with the basic Newton's second law. So total force or net force in some direction, we'll just say the x direction, is equal to mass times acceleration in that direction. We're relating a force to some motion. So this is a logical step to do. So this has force and it has a bit of something moving. So we can bring in velocity into this equation. We can relate to velocity. This is assuming that we have a constant acceleration. Assuming a constant acceleration. So this is where we just take something we've learned about constant acceleration. We had those kinematic equations. We're going to take one of those, and we're going to take specifically this one. Says like V final squared is equal to V initial squared plus 2A in some direction times the displacement. We will solve for this acceleration. And substitute that into that top equation. Let's solve for acceleration. Acceleration, that's 1/2 delta x. And all of this times final velocity squared minus initial velocity squared. And I'll say substitute into that first equation up here. To first equation. So by taking this acceleration term, putting it into that equation, we'll end up with, I don't have to go every step. We'll just go like this. The force in some direction, x, is equal to, the force times some displacement is equal to 1/2 mv final squared minus 1/2 mv initial squared. This is, now if you look at the first part of this equation, sort of this left-hand side, my first page of the notes today, I saw that this is work. Force over some distance is just work. So we say, we know that's F times some distance is just work. That's the energy. So we have this way of relating work to an object's movement. Not just a force and a position, but a velocity as well. Final minus 1/2 mv initial squared. Okay, let me put a little star next to this. This is where we say, what if, we have something that's like at a constant speed? Well, the work will be 0, but we still have, why is this term popping up twice? It's where we can define kinetic energy as this term. We could say kinetic energy or the energy of a moving object equals, I may write it KE. Some videos or other books, it could be written as just K. I think your book says it as just K. Kinetic energy, the equation is just 1/2 mv squared. 1/2 mass of an object times its velocity squared. And we have this way of relating kinetic energy, how an object may move. We could get this, velocity and go directly into energy. We don't have to do that 4-step process all of the time. And I'll say at the bottom, we have this relationship between work and kinetic energy. So we have the work kinetic energy theorem. If you look at this equation, I have the star next to. That's just the final kinetic energy. So the final kinetic energy minus the initial kinetic energy. It's all related to the object's velocity. So, an object, you expect it to have the same mass as it moves from one place to another. So the mass you may expect to remain constant. That's not always the case. For like a rocket, or even in the most technical case, like a car, it's going to be using its fuel while it moves. It's more dramatic with a rocket. It's burning up a lot of the mass as it propels itself. In this case, I'll just say work total is equal to the change in kinetic energy. We'll say delta K. We'll keep it as just K because that's how your book has it right now. All right. So that is as far as I want to get for today. I'm going to continue chapter 6 tomorrow, and I'll get through chapter 7 by the end of this week. And next week, we're not having a quiz, we're having an exam. So the exam will be on all the previous material, as well as this material. So chapter 6 and chapter 7 that I'm going to cover this week. So it's only going to be, it's going to be all of this material. I'll give you guys sort of a lot more time to do this exam. I'll put more information in like an announcement on Friday over what you guys can expect. Yeah, let me get you guys ready for your quiz today. They'll be on the last or chapter 3 and chapter 4.